Okay, so we already know that in this course can be divided into two parts. The first part, which is combinational logic circuits, and we already done this, which is including the decoders, multiplexers, encoders, AND gates, logic gates, all of the basic logic gates, which is any design, there is no time with it. While the second part, which is sequential logic circuits, and then this part there should be storage elements. Then in that storage elements, which is we call them flip-flops or latches. Then after that, after including the storage elements, we can create registers, counters. Then all of them were part of the circuits. Now we need to make some how to make the design. Last lecture or the previous lectures, we already explained some analysis on this, which is when we have an existing design, how can we make some analysis, which is how can we find the state table and state diagram. And also when we discuss about the state table and state diagram, there was some examples, which is some design examples, how to find the state table and state diagram for this one. So we already familiar how to find for a written problem, how to find the state diagram and state table, and we're already familiar with the existing design, how to find the state diagram and state table. So, for example, the Cook machine design, we already know how to make when to release the Cook, when to release the change, and so on, or to detect a certain sequence of bits. So we can build this program and make it based on state table and state diagram. And again, previous examples, even in the last quiz, we already have an existing design. We already know how to convert this back into a state table or state diagram. Now, how about the opposites? If we already have the state table and state diagram, we need to build the circuits. Or how about if we have a verbal or like a written problem, and we need to build it to the end, not only to make a state table or state diagram. Like the Cook machine example, after building the state table and state diagram, we need to have the other step, which is building the hardware circuits. So it can be ready to complete my design and I can finish it. Then this is what will be done with the course, which is make a completed design. Start from the scratch, I have inputs, outputs, then convert this to a written problem, then convert the written problem into state diagram, state table, which is very similar to truth table, but state table, which is including next data or next states, while truth table was input and outputs. Now we have next state, inputs, next present states, outputs, next state, something like that. So the state diagram is very similar to the truth table, because there's time dependent. Then after converting this, we will make it as hardware circuit. So in this chapter, we expect to see the completed design. However, I have separated this chapter into two parts. The first part, which is the analysis, which is we have the circuits, given circuit module, we need to determine the output and the input sequence. We already done this, we're already familiar with this part in the previous even, and again, like last quiz was part of this one, which is we have the circuit existing design and we need to make a state table, state diagram. Then after that, which is the design, the second major parts. So our targets, we will go back first, like do some analysis in today's lecture. Then starting from next lecture, we will go to the design problems. Okay? Then in design problems, we expect to do multiple design or different designs, so we can do many things. Okay, let's go to part one, which is the analysis. How can we do the analysis? So most likely, if the state diagram or state table is provided, then we can skip everything. We will go to step number 6, 7, 8, and 9. If it is not, we need to determine the state diagram, which is the first, most likely you need to determine where is labeled the inputs and the outputs. Then after that, we can, here is one way, which is constructing K-maps for all logic equation circuits. then combine the care maps into flip-flops to combine into single map, then construct the next state map, then construct the binary state table by combining the next state map, then draw the state diagram, then state table, then we can make the waveforms or the time flip-flop forms. Then in the timing diagram, we can plot the other waveforms in case if we need to do the rest of waveforms. Okay, let's look at this example. We need to do the timing diagram for this one. So here we already have the state table and the state diagram. So the problem can be easier for us to follow. So giving the state diagram that uses a negative edge trigger. Keep in mind this is negative edge. This means it is falling edge. So the update will happen only at the falling edge. Trigger flip-flops determine the output's response if the initial status is 0, 0, and if the input is 0, 0, 1, 1, 1, 0, 1, 1, 0. So here is the clock cycle. Here is the inputs. Then we need to find Y1, Y2, and Z. Y1 and Y2 are associated with the states. Z is associated with the outputs. Now, how can we make our analysis like this? Most likely, we need to make sure it's falling edge. So here is falling edge, the update's happening here. Falling edge, falling edge, falling edge, falling edge, falling edge, and falling edge. The inputs has already been given like this. So the initial status is given for as 0, 0. So we will start from 0, start from 0. Then the initial condition also for the output is 0. Okay. Now, the analysis for this one is very easy. So first part, make sure to locate the points that there will be updates. So until here, everything will be this one. This is very similar to what we did even in the exam, in the second exam, but here it's kind of more complicated than that. So let's see. Now our initial condition at 0, 0. We are at 0, 0. Now the inputs is 0. If the input is 0, what's the next state? Will be at 0, right? And the outputs is 0 as well. Is that right? So we will be at 0, 0, and the output is 0. Then the next updates here happens also at 0, 0 here. So we are here at 0. So what will happen if the input is 0? We will back to 0, right? So we will be still, the state will be 0. The next update of the states will be at the next trigger edge. While, remember, the output, this is Mealy model. The output is a function of both time and states, right? So here the input has been changed in the mid-cycle. There is a mid-cycle change, which matters for us, right? This mid-cycle change will make, sometimes can make change on the outputs. So how can it make change? Look at 0, 0. So we said that initially will be 0. Now the input will be 1. If the input will be 1 in the mid-cycle, the input will be 1, the output will be 0. So there's still 0. Even there is change, but at that change, the output will be 0 in both ways, right? So it will remain 0. Even in this mid-cycle change, they will remain 0. Okay, do you agree? Now, here at T2, the input is 1. So we are still at 0, 0. The input is 1, so it will go to 0, 1, right? So in 0, 1, remember, this is y2, y1, here is y2. This will make y2 will be, remember the order, here is the order. So y2 will be 1. So what will happen? y2 will go to 1, and y1, here is y2, will go to 1, while y1 will be 0, will remain 0, because we'll go to 0, 1. Clear? Then, what will happen to the outputs? The output here is 0, so it will remain 0. Is there any mid-cycle change? No. Then it will remain 0. Okay? Clear? We're already familiar with this. It's just like you can consider it as a review, but with complicated or comprehensive example. So we have 0, 1, 0, 1, 0. Then there is a cycle at T3. There's a change at T3. Now we are at 0, 1. So let me erase this. We are at states 0, 1. The input is 1. So according to here, to this arrow, if the input is 1, I will remain at the state which is 0, 1, and the output is 0, right? So it will remain at 0, 1. The output is 0. Is there any mid-cycle change? No. Then it will remain 0. Then at T4, it's the same way. Remain 1. So I will remain at the same states. No change. Okay, clear? Then there is a mid-cycle change here. So this might or might not affect depending on the status. So here it will be 0. Then let's go to 0, 1. If the input is 0, the output is 0. So this mid-cycle didn't change a lot, right? So it will be the same. It will not affect it. It will not be affected. So here is 0. Okay? Then at T5, now we are now at T5. Let me erase everything. We are now at T5. With T5, the input is 0. Let's follow. We are at 0, 1. The input is 0. The output is 0. Then the next state will be 1, 1. This will make both y's will be 1, 1. So I'm going to update this y1 to be 1. y2 will remain 1. Okay. What will happen to the outputs? The output is 0. Therefore, it will remain 0 as well. Okay? Then, look at T6. At T6, okay, is there a mid-cycle change? Yes, I forget this mid-cycle change here. There's a mid-cycle change that might or might not affect. So here the input is 0. Then this mid-cycle change might or might not affect into the outputs. So it will be, we are now at 1, 1. So our states currently is at 1, 1. When we are at 1, 1 in this state, the inputs, if the input is 1, the output will be 1. So here, at mid-cycle change, the output will go to 1. Okay, do you agree with me? Because it is a mid-cycle change. Again, this is merely model. If it is more model, don't worry about the change, because the output will be function of states. But now, the output is a function of states and inputs. So there is a mid-cycle change in the output. So now they are all 1s. 1, 1, 1. Now at T6, we are at T6 now, and our input we are at 1, 1. If the input is 1, it will remain. It will hold at this state, right? If the input is 1, it will remain, and the output will be 1. So it will remain at 1, 1, 1. 1. 1, and the output is 1. Because according to this, if it is 1, the output is 1, will remain at 1, 1. Okay? Then, after that, at T7, it is 1, then it will be the same scenario. It will remain for the states. 1, 1. Look at the outputs. or look at the input, there is a mid-cycle change. So this might affect, might or might not. So we will see. So here the input will be 0. We are at 1, 1. At 1, 1. If the input is 0, the output will be 0. So it will be moved to 0. Okay, clear? Then at T8, there will be another update. So let's see at T8. We are at 1, 1. The input is 0. The output is 0, and we will go to 0, 0. So this will make y1 and y2 zeros, and the output is 0 as well. Okay? Then the last update at T9, we are currently at 0, 0, which is here. This is 0, 0. If the input is 0, the output is 0, and we will remain at 0, 0. So here's the input is 0. This will make everything zeros. Okay? Therefore, as a result, we can say the output sequence will be 0, 0 each cycle. So this cycle is 0, this cycle is 0, this cycle is 0, 0, 0, 0. There is a mid-cycle 0, 1. Here is 1. Here is 1, 0. Here is 0, 0. So 0, 0, 0, 0, 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Then here is 0, 1 with mid-cycle change. There is 1, 1, 0, 0, 0. I make it like this because there is a mid-cycle change. Okay? Any question? Yes?
If you're setting up an X, do you always do the change in between the clock cycles?
Most likely, here in this diagram, we assume there will be change in the mid-cycles, but most, I'm not sure like how will it be in real life, but sometimes it can be, if it is going to be change in the mid-cycle, it should be provided. So you will not assume, or you don't know actually where is the change. So for example, in this sequence, it's given x 0, 0, 1, 1, 1, 0, 1, 1, 0, something like that. So here, if you have this sequence without having this input, so you will assume, if you have the choice, you will assume the change happens only at the trigger edge. But here it's given, so I would like to remind you there is a mid-cycle change. But again, in case if there is no, if the updates, or if you have the choice to select X based on the given information, then you can assume it only the updates happen at the positive or at the negative trigger edge. Therefore, you don't need to worry about any mid-cycle change. Actually, it will be much easier. Okay, any other question? Okay, let's look at this example. Consider and construct this equation. Actually, I would like to say that the notes that's here, the procedure, those are from the textbook. But sometimes I can say, I don't need to use every time K-maps. I can use sometimes something easier. Or I can construct K-maps. It depends. So let's go to this part. How can we make the analysis for it? Very similar to what we got in the previous lectures when we did the quiz as well. So we need to consider this example. Let's see how we can follow it. So here is X. So here it is, we call it Y uppercase, which is the next state, or we can say Y star, and here is Y, the current state. Then here is Z, this is X bar, here is Y, then in this part which is Y bar, so this is going to be X, Y bar, here is X bar, Y. So Y star will be X, Y bar, plus x bar y. Then what else? Z, we can say it is x and y. So as a result, we can say z equal to xy, and y star, or y next state, will be xy bar plus x bar y. We can realize that here the outputs is, let me write the output as output, is a function of state and inputs. Therefore, of course, we're going to use Mealy model. We cannot use Moore model. Use Mealy. Cannot use Moore model. When you draw the state diagram, when you do the state table, I encourage you to use the generalized table. Okay? So now we have the equations. Z equal xy, y star equal to x, y bar plus x bar y. So how can we do this? If you follow the textbook, sometimes you can do it using K-maps. Sometimes I prefer, when I do it, is not to use K-maps. There's an easier way, which is do the generalized table, which is we have present state, as we did earlier here, which is y. Then we have next states, which is, we have inputs, then next state. Inputs, which is x. Then we have next state, which is y star. Then we have the output, which is z. So you will consider, before the two parallel lines, consider them as a truth table. So which is going to be like 0, 0, 0, 1, 1, 0, 1, 1. So you can, for example, say the zeros are state A, the ones are state B. Okay? You have only one flip-flop. How many states? 2 power 1, then 2 states. Number of states equal 2 power number of flip-flops. So 2 power 1, which is 2 states. And this can be called A and B. Okay? So we have A and B, as shown here. So 0 for state A, 1 for B. Then what will happen to the next states? You can use the equations that we have. So the equation z equal xy, 0 times 0, 0, 0 times 1, 0 for z. 1 times 0, 0, 1 times 1, 1. That's for z. For x, it will be xy bar plus x bar y, which is exclusive OR. Then count the number of ones. If it's odd, will be 1. If it's even, will be 0. So it will be 0, 1, 1, 0. So now we did this. So I think doing this one is simpler than doing the K-maps or doing the textbook method. Maybe other instructors teaching this one in a different way, but that's why I prefer. So it can be much easier. It can be more convenient because we already construct this table many times. And we already know how to do this state table. So that's it. You already have the state table. Why do I need to convert the state table to K-maps? Fine, so that's... Now, how to do to draw the Mealy model diagram. So again, we said that 0, 1 or state A or state B. So we can say A, or in other words 0 here. Here is state B, or in other words 1 in this bubble. Then we can follow. If the input is X, if the input is 0 at state A, we will remain at 0 and the output, which is Z, 0. If the input is 1, we will go to next state, which is 1, and the output is 0. Now with the state B, if the input is 0, we will remain and the output is 0. If the input is 1, we will go to next state which is 0, but the output now will be 1. That's it. So there's the battery. Okay, so there is another way that can be done using K-maps, just for your information. So if you prefer the other way, it can be fine. Which is the other way that the textbook uses, which is using K-maps. So we already have the first equation, which is y star equal x, y bar plus x bar y. And we have the other equation z equal xy. So we need to have each kernel map for each one. Kernel map for this, for y star, kernel map for xy. So we have two variables, then two variables kernel map. Yes?
Is that bottom line coming from b equals 1? Is it supposed to be 1 over 1 or 0?
1 over 1, yes. Thank you. I apologize. It should be 1 over 1, yes, correct. Thank you. Now, we need to have a K-maps for each one. So here is y, here is x, here is 0, 1, 0, 1. Then the same here. Here is y, here is x. It's two variables, so 0, 1, 0, 1. Now, x, y, in terms of min terms, is equivalent to 1, 1. Therefore, it is M3. Y bar, this is 1, 0. X bar y 0, 1, then this is equivalent to M3, M2, and M1. M1, M2. So when you construct K-maps, here is M0, M1, M2, M3. Then here is M0, M1, M2, M3. We know how to deal with kernel maps. So with y star, it will be at M1 at M0, M1, M2. Then here, the 1 will be at M3. So how can we do this to write this into merely, not the generalized model, merely model state table, which is including, here is the present state, y, here is input, which is can be, here is input x, it can be 0 or 1. This is the model that we used to do with the in MIDI model. So how can we deal with this? Most likely we used to put, like, as I said, like 0, 1 and the state here 0, 1. Then look here, we can put zeros for the missings. Then those are zeros. So we have 4 squares. Copy these squares here. So we will copy the first sets. It will be 0, 1, 1, 0. Then we will put slash for the outputs. After that, copy this here. Then we will put here zeros, 0, 1. This is the textbook method. Okay? Then just put kernel maps inside this diagram, then it will be easier like this one. So whatever you like, you can choose. Then from this merely model state table, you can convert it to the generalized table, or you can keep it as is. Either ways are fine. So you have the tool, you have the options, so it's up to you. Then later we can say this is state A, this is state B. So we can rewrite this as present state. This state A, this state B. Here is inputs. X here is 0, here is 1. then we can say here is, instead of 0, we'll say A over 0. Here is B over 0. Here is B over 0. Here is A over 1. Then this is in other words. That's if you need. You can give the meaning for, or give a name for these states. Then it will be the same way as this one. But here, like, we didn't replace zeros by ones, by A's or B's. Yeah, I think this is repeated what I said. Now, let's consider this diagram, this input already been given. The waveform of this input is already been given. So we need to calculate the present state. Let's assume the present state is 0. We need to calculate the next state and the outputs. So those are, again, the present states, y. Actually, why do we need to make, we don't need to make it y star. Let's make it y, which is for the states and the outputs. States and outputs. So the state is 0. Let's assume it's triggered at the positive edge. If there is no information, again, assume the default, which is positive edge trigger. How we can make the analysis? You have the equations, or you have the already written the state diagram, which is A and B. Let me rewrite it here. 0, 1. So here is 0 over 0. Here is 0 over 0. Here is 1 over 0. Here is 1 over 1. Now the initial state is 0. So we are here. Then the inputs is 0. Let me write the values of the inputs. Here is 0, 1, 1, 1. Okay. So here the input is 0. Now initial state is 0. The input is 0. So what will happen? We will remain at 0 while the output is 0. So we will remain at 0 and the output is 0. Keep in mind there is a mid-cycle change here. So it will be, the input will be 1. Since the input will be 1, look at here. The input is 1 at state 0. The input is 1. The output will remain 0. So this mid-cycle change will not affect in the outputs. So it will remain, output will remain 0 even with this mid-cycle change. Now at T2, the input is 1. So we are 0, the input is 1, output is 0, it will move to state 1. So Y will be 1, the output will remain 0. Y will go to 1, the output will remain 0. There is no mid-cycle change. Then here, it will be 1. This means the same will be 1. The output is 0, but there is a mid-cycle change. So this mid-cycle change, which means it will move. Okay, let me see something. I think I messed up with something. Okay, I said the input is 1. Again, we are here. The input is 1, output is 0. We will go to the states. So what will happen? This state will be 1, output will be 0. Right? Then at the next updates, we are at 1. The input is 1, outputs will be 1. Right? So this will make some differences actually, which is here. The state should be 1. I apologize about missing this. Because here state is 1. Input is 1, so output is 1. Then here this updates, since it's 1, it will go to 0. It will go back to 0. The state will back to 0 because when it's 1, it will back to 0. Then what will happen to the outputs? Since the state is 0, the input is 1, it will back to 0, and that middle cycle change, we are at 0, and with 0, input 0 will keep it 0, like this way. Then what? Let's keep going. So here we have the input is 0. At this states the input is 0. The input is 0 will remain, the output will remain 0, and will remain the same state, which is 0. There is a mid-cycle change, so we say that the output is 0, and at mid-cycle change the input will be 1. If the input will be 1, the output will remain 0, so there is no effect on the output, it will remain 0. Then the output is 1, we are at state 0, the output is 1, we will go to 1. So the state will move to 1. What will happen to the outputs? We are at state 1. The input is 1, so the output will be 1. There is a mid-cycle change, so because now it will be from 1 to 0, which make it 0. The input will be 0, so the output will make it 0. Okay? Then, here is the updates. It is 0, so the input is 0. We are still at state A. The input is 0, the output is 0, and we will remain at 1. So if the input is 0, we will remain at 1. Input is 0, remain at 1. Input is 0, remain at 1. While the outputs, since 1 and 0, we are remaining at 1, and the input is 0, so the output will be 0s for the rest. So it will be 0, 0, 1, 0, 0, 0, I think here there will be a change, 1. Let me see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. We have 8. 1, 2, 3, 6, 7, 8. So we have the first one appeared, but there is one in the mid-cycle change, which is going to be updated. Here, 0. 0 is the initial condition. Then here is 0 with 1, and so on. So we will realize this thing, this mid-cycle change, sometimes they call it a glitch. It's called a glitch because there is some change happening during the mid-cycle. And this is sometimes something we don't prefer. That's why sometimes you'll see in the textbooks called as a glitch. Let's forget about this. I think this one is incorrect, this sequence, so let's consider this one. Now, another example number 3. Then, yes, we will be done with these parts. It's just like analysis. So, analyze the following circuits, then draw the timing diagram to show the circuit response with this input. So here is this circuit. We need to find the state table, state diagram. After that, this is the timing diagram. We need to find the other elements, other factors. So let's look at this one. So we see here, look at the outputs and look at the states. So let's see, here's the inputs. Here is X. Here is X bar. Then here is X. Since X bar goes here, X bar goes here. Then here is Y2. So this is x, y, 2. Then here is x bar, here is x. Here is y1 bar, x bar. So it will be ORing, which is x bar plus y1 bar. This is K2. So now we know J1, K1, J2, K2. Then we can say within Z is actually will be Y1. What's the other? Y2. Y1, Y2. So we can realize that the output here is a function of states only. It's not a function of output inputs. So we can say that in case if we need, we can use more model. We can use more model here. If you want to use meaning, that's fine, but we can use more model. And we don't expect to see mid-cycle change, right? Because in more model, it outputs function of states. So we can say this notes, we don't expect to see mid-cycle change, or in other words, no glitches. We will not see glitches, that anything, which is making it much easier. How can we analyze this? So let's write the equation here. We have J1 as xy2, K1 as x bar. Then we have J2 as x, K2 as x bar plus y1 bar, right? Then, and we have Z as y1, y2. So how can we make analysis? Let's recall they are JK flip-flops. So with respect to y1, we can say y1 star is J1 y1 bar plus K1 bar y1, right? Substitute the values. So J1 xy2, so it will be x y2 y1 bar plus K1 bar is x bar, so it will be x bar y1. So this is y1 star. To make it in the right formula or right standard alphabetically, which is x y1 star y2 plus x bar y1. This is y1 star. Then we are done with the first one. The outputs, we already know y1, y2. So we are done with the outputs. Then the other equation, which is related to the y2, y2 star equal to j2 y2 bar plus k2 bar times y2. Substitute j2 and y2. j2 is x, so it will be x y2 bar plus k2 is actually x bar plus y1 bar, all bar times y2. Apply De Morgan's on it, so it's going to be x y2 bar plus x bar. Bar will be x, addition will be multiplication, y1 bar, bar will be y1 times y2. That's y2 star. Okay? Do you agree with me? Now, when we have this, we have the choice to make the equation like this, y1 star, y2 star, or we can actually calculate j1 alone, k1 alone, j2 alone, k2 alone, then do the design. So let's do the state table. State table, here is present states, which is y1, y2. Here is inputs, which is x. Then there are two parallel lines. Then here is next states, which is y1 star, y2 star. Then here is outputs, which is z. Since I'm using JK flip-flop, sometimes as a shortcut, instead of using that long equation, we can calculate J1, K1 alone. So I'm going to add two parallel lines. So for the flip-flops, we have J1, which is actually was XY1, XY2. And we have K1, which is actually X bar. Then we have J2, which is actually X, and K2, which is X bar plus Y1 bar. Okay? Now, how can we construct this table? Again, make it as a truth table. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And actually, you can call this states 0, 0. Since we have two flip-flops, 2 power 2 equal 4 states. And I can call them A, B, C, D, which is 0, 0, 0, 1, 1, 0, 1, 1. So this one can be called as state A. These can be called as state B. This can be called as C. This can be called as D. Then, state A with input 0. So what will happen to the next state and to the outputs? So the output, as we know, it is y1 times y2. So we can find z actually easy. 0 times 0, 0. 0 times 0, 0. 0 times 1, 0. 0 times 1, 0. 1 times 0, 0. 1 times 0, 0. 1 times 1, 1. 1 times 1, 1. So we can calculate the output easy. So we are already done with the outputs. How to do the y1, y2? It's JK flip-flop. So what if you can either use the equations that we already found here and here, or you can find J1, K1, J2, K2 alone, then it will be easy to do it with flip-flop. So J1 is actually X, Y2. 0 times 0, 0. 0 times 1, 0. 1 times 0, 0. 1 times 1, 1. 0 times 0, 0. 0 times 1, 0. 1 times 0, 0. 1 times 1, 1. So that's how it looks like J1. K1, look at X and it's the opposite. So X 0, 1, 0, 1, Z1, so it will be 1, 0, 1, 0, 1, 0, 1, 0. J2 is similar to X. So it will be 0, 1, 0, 1, 0, 1, 0, 1, the same as X. K2, which is X bar plus Y1 bar. Look at X, the opposite with it, which is like K2. You can look at this. Then plus Y1 bar. Look at Y1 and make it the opposite. So Y1, 0, 0. The opposite, which will be 1. 1 plus 1, make it 1. 0, the opposite 1. 1 plus 0 will be 1. 0, here, this is 1. This will be 0. 1, which will make it 1. This is 0. 1, which will make it 0. This will make it 0. Then here, 0. Since this zeros, this will be the bar. I think I should look at here. At y2, okay. Y1 bar. Yes, so it will be 1. We'll make it 0. Then here, but here, there is 1, so it will be 1. So 1 will make it 0. Then since there is look at X bar, will make it 0, so it will be 0. Then dy1 bar, which make it 1. This will be 0. So the last 4 zeros. Let's look here. 0, 1, 1, 0, 1, 0. So on y1, let me double check. X1 bar plus y1 bar. Okay. Yeah, so it will be the first one, since all of them are ones. I think they'll double something. Okay. Because actually, when y1 equals 0, this will make it K2 equal to 1. Because 0 bar will be 1, then 1 plus any number, it will be 1. So the first 4 rows will be 1. After that, when y1 is 1, K2 will be x bar. So it will be the opposite of x. So here 0, 1, 0, 1, it will be 1, 0, 1, 0. Okay, that's it. After that, we need to apply JK flip-flop for y1 and y2. So how can we achieve this? Then basically, we can say that any flip-flop, JK flip-flop, Q star will be J Q bar plus K bar Q. Okay, let's look at y1. y1, when y is 0, when y1 equals 0, what will happen? J Q bar, which is, let's substitute, Q is 0, so it will be y1 star will equal to J. When y1 equal 1, then y1 star will equal to K bar. Okay, so here is y1. The first 4 rows for y1 are zeros, then y1 star will be as j1. So let's substitute the value of j1 on at y1, which is 0, 0, 0, 1. 0, 0, 0, 1. Then we are done with the first part. The second part, K bar. Look at K1, it will be the opposite. So it will, here it was 1, 0, 1, 0, it will be 0, 1, 0, 1. 0, 1, 0, 1. Then we can, the same thing we can apply it for y2. It will be j2, k2. For the first 2 rows, y2 were 0, so it will be the same as j2. j2 here was 0, 1, so it will be 0, 1. Then the second row was 1, so it will be k2 bar. So it was 1, so this will be zeros. Then the third row, it will be the same as j2. The third quarters, which is going to be 0, 1. Then the last one, which will be the opposite, it will be 0, 1. Finally. Now look at the states. 0, 0 is the same as state A. 0, 1, B. 0, 0, state A. 1, 0, states C. 0, 0, state A. 1, 1, state D. 0, 0, states A. 1, 1, state D. Right? Then we can construct the diagram, which is called the state diagram, and let's use Moore model. Moore model with the state D, you will see 1. With state C, you will see zeros, B zeros, A zeros. So the outputs will be 1 only with the state D. So we can say, write the 4 circles, A, 0, B, 0, C, 0, then D, 1. Then in this situation, I don't need to worry about the output, so I already included it here. Let's look at state A. If the input is 0, it will remain at A. If the input is 1, it will go to B. Now with state B, if the input is 0, it will go to A. If the input is 1, it will go to C. Now with state C, if the input is 0, it will back to A. If it is 1, it will go to D. Now with D, if the input is 0, it will go to A. If it is 1, it will remain at D. Then that's it. This is in Moore model. Okay, clear? Now, how about the timing diagram? like this. Let's assume x is already been given. Here, I'm not gonna worry about drawing J2, K2. Let's worry about how to draw Y1, Y2, and the outputs, Z. So we have 0, 0, 1, 1, 1, 0. Let's assume, already given in the question, the initial states 10. So I think this is Y1, here is Y2. Y1 is 1, Y2 is 0. So the initial states, Y1 is 1, Y2 is 0. Okay, so Y1, 0, this means state C, right? 1, 0, state C. At C, what's the output? Look at C, the output is 0. So the output is 0. Now, the updates, I think it's already been given, the updates is negative edge. No information is negative edge, but we realize this by looking at the clock cycle. So we can say it is falling edge or negative edge. Therefore, keep in mind you need to draw the guidelines for the negative edge. Let me write them. Okay. Now, before the first updates, this is 1, this is 0, this is 0, we are in state C. Then the next updates, we are at 1, 0, which is state C, the input is 0. Let's go here. We are at state C, the input is 0. Where should we go? We will go to A, and the output is 0. And that's what we will do. If the input is 0, we will go to A, which means both of them will be 0, 0, 0, the output is 0. Okay? Then we are at state A, the input is 1. Here is state A, input is 1. We will go to B, which is 1, 0, 1, and the output will be 0 as well. At state B, we are at A, it will go to B. B means 0, 1. And the output will remain 0. We are here now at state B. Okay? Then, we are at state B, the input is 1. B, input is 1, we will go to C. And the output will be 0. Right? So we will go to C and the output is 0. So I'm going to draw it here, which will be, it will go to 1, 0, because this state C, the output will remain 0. Now we are at C, the input is 1. We are at C, the input is 1, so it will go to D, the output is 1. Whenever I'm at state D, the output is 1. We will go to state D, and the output is 1. What will happen in state D, which will be a kit? 1, 1. Now we are at state D, the input is 1. State D, input is 1. We will remain at D, right? That's what will happen. And the output is 1. So we will remain at D. The output is 1. Then here, we are at state A. We are at state D. The input will be 0. Let's go here, D. D. The input is 0. We will go to A. The output will be 0, right? So it will go to A, which is 0, 0, and the output is 0. So everything will be zeros. 0, 0. I think I need to draw the ones here. I forgot. Ones should be up. Okay. Then here's state A. Then we are at state A. The input is 0. We will remain at state A with the output 0. So everything will remain zeros. Which will remain at state A. Okay? So we can say for the following sequence, x equals 0, 0, 1, 1, 1, 1, 0, 0. Actually, let's see. We have 7 pulses. 1, 2, 3, 4, 5, 6, 7. Let's forget the last one. So the sequence, corresponding sequence, will be for the 7 pulses. So here, let me call it, this is T1, T2, T3, T4, T5, T6, T7. Add those pulses. Here is T1, T2, T3, T4, T5, T6, T7. You see the last one will not be included because it will be for the next cycle. So let's make it like this one. So here Z will be 0, 0, 0, 0, 1, 1, 0. Then the sequence states sequence will be C, A, B, C, D, D, A. Okay? Is this clear? Any question? So you see the analysis, we are aware of this in the past, but it's getting kind of more tough, more complicated, but if you follow the procedure, it should be all right. Again, I did this state diagram based on what I wrote here, the method I wrote here. But if you want to use K-maps, you can use it here. How? Let me use K-maps into these equations to make the state table so you have a clue about different things. So the equations that I just derived, let me write in different colors using K-maps. So Z equal to Y1, Y2. And we got Y1 star it was how much it was? XY1 bar Y XY1 bar Y2 plus X bar Y1. XY1 bar Y2 plus XY1. That was for Y1 star. Yes, Y2 star, XY2 bar plus XY1 Y2. Y2 star, XY1 bar plus XY1 Y2. This is XY1 bar, XY2 bar, yes. XY2 bar, not XY1 bar. Okay. In order to make it in the canonical form, there's a missing variables here. So it will be Y2 plus Y2 star. And there's a missing variable here, which is Y1 plus Y1 star. To make it into the three forms, three variable K-maps. So it will be X, Y1 bar, Y2 plus X, Y1, Y2 plus X, Y1, Y2 bar. So this is equivalent to 0, not zeros, 1, 0, 1, 1, 1, 1, 1, 1, 0, which is in min terms, this is M7, M6, M5, 5, 6, 7. While for the other one, it will be X, Y1, Y2 bar plus X, Y1 bar, Y2 bar plus x, y1, y2. In min terms, this is equivalent to 1, 1, 1, which is M7. This is 1, 0, 0. This is M4, 1, 1, 0. This is M6. Then we can do k-maps. We can do 3 k-maps actually for each variable. For z, y1 star, y2 star. Let's construct 3 k-maps, 3 variable k-maps. It's going to be like this. Here is y2, x, y1. Zero, 1, 2, 3, 4, 5, 6, 7. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. The same here, y2, x, y1. Actually, let me finish writing this. This is equivalent to x, this is equivalent to y1. Can I copy this? Uh-oh. I'm not sure. How can I copy? Okay. I need to redraw it. Let me redraw it. y2, x, y1. So you're 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So 0, 1, 2, 3, 4, 5, 6, 7. Here is 6, here is 7. 0, 1, 2, 3, 4, 5, 6, 7. So we can say that the location of ones here is variable z, here is variable y1 star, here is y2 star. Z, to make it into the complete formats, it will be x, y1, y2 plus x bar, y1, y2, which is going to be 1, 1, 1. This is 7. This is 0, 1, 1, which is 3. M7, M3. So for Z, we have 1 at M3. What's M7? For y1 star, we have 5, 6, 7. 5, 6, 7. While for y2 star, it will be 6, 4, 6, 7. 4, 6, 7. Okay. So how can we make the problem easier, or how we can make it convert this into the state table? Let's construct the state table using Mealy model. We have here present states, which is here y1 star, y2 star. Here's inputs. How many inputs we have? 1, which is x. Input x, we have 0, 1. And here is outputs, which is related to the present states. Output z. Okay, how we can drop this here? Actually, I think we need to look at this diagram look at the k-maps, make the observation like this. I mean flip it. So for the present state, we have 0, 0, 0, 1, 1, 0, 1, 1. So you can, again, what do I mean by flip it? You can look at this side like this way. So here's will be y2, here's will be x, y1. Or actually, I think we need to make it like the other way, which is this way. x, y1. Here is y2. So the counting will be like this: 0, 1, 2, 3, 4, 5, 6, 7, or okay, I think I need to revise this. Okay, I think we are running out of time now. I need to revise this, but we need to make sure that to flip it, to make it into this sides, all of them. Then we will, I'm not sure about the order, but after like checking the order, we can put them here. This is for Z, this is for X, and so on and so on. So we'll continue this later. Thank you.